Right, we are in lesson 8 with our MPU6050 sensor. You'll find this information in our repository module MPU6050, lesson 8. All right, what we're going to talk about in this lesson is how fast we can actually sample the measurement data. Right, in working with this sensor, we've been using the default configuration of the config register, which when we look at the register map, that shows us the sampling frequency of the accelerometer is 1 kilohertz, the gyroscope is 8 kilohertz, right? And so these limitations are imposed by the sensor hardware, but can our program keep up with that? Right? We talk to this via I2C communication. So what are its speed limitations? All right, so when taking a look at the practical limit for reading this data, right, I want to remind you then, we've been using the Arduino wire library. Its standard mode clock frequency is 100 kilohertz. That's what we've been using. So let's take a look at how much data we can actually read at that frequency. All right, so I2C serial communication transmits one bit for each clock cycle. So 100,000 clock cycles, 100,000 bits. So 100,000 bits in a second at 100K hertz. Right. Now we want to take a look at what I2C is transmitting across there. Right. So each data frame is going to have 8 bits per data byte, and it's going to be followed by an acknowledgement bit. Right. So for 9 bits, that's going to require a total of 9 clock cycles. Right. And so whenever we initiate transfer from the master, so Arduino is the master, the MPU6050 is the slave, we then have a start condition. Once the master signals that start condition, we've been working with a 7-bit address. So that address goes across that 7-bit address frame. And then the next thing we send is a read or write bit to tell it, of course, whether we want to read or write. And then that is followed by an acknowledgement bit. After that, then we start sending data frames that are 8 bits wide, followed by an acknowledgement bit. So that cycle continues until the read and write is complete. And then the master issues a stop condition. So let's take a look then. Right, here is what we've been using to read and write, the code we've been using from the measurement registers. Right, you can see we begin that transmission. So here's our address, that hex 68 we've been using. And then the next thing we do is our first data frame. That's the register that we want to read from. Right, there's some overhead here with this end transmission. Right, we're actually saying to the slave, don't end the transmission. We'll let you know when it ends, right? Because we want to request some bytes. And so we have the overhead of this function call requesting the bytes. We want 14 data bytes so that we can read all of the measurements out. All right, so let's take a look at the clock cycles that relates to across I2C. Right, so the I2C address is 7 bits. We have 1 bit for the read write, and then followed by the acknowledgement bit. Right, then the register number is 9. 9 because it's a data frame, and we have that ACK bit at the end. And then for each one of these measurement fields, we have 18 bits because we need 2 bytes for each one of these fields. Each byte is followed by that ACK frame. So 9 bits per byte, you can think of that. And so we have 18 for each of these fields. So when you total all of this up, it's going to total 144 bits. There's 1 bit per clock cycle, so 144 clock cycles. So at 100 kilohertz, 144 clock cycles then is going to require 1.44 milliseconds. Well, if we're trying to read things at 1K hertz, that's not going to do the job, right? Because that time period corresponds to a frequency of approximately 694 hertz. That's much slower than our 1K hertz sample rate that we'd like. And that doesn't even consider some additional overhead time that's going on in the Arduino itself with the programming. One thing we're going to keep in mind as we walk through these examples is that the MPU6050 will support I2C fast mode clock frequency of 400 kilohertz. So we'll take a look at how that 400 kilohertz helps us, right? But theoretically, if we just look at it, 144 clock cycles at 400 kilohertz will only require 0.36 milliseconds, which corresponds to a frequency of about 2778 hertz. So that 2778 hertz, right, is faster than our 1000 hertz or our 1K hertz. So it looks like we should be able to read through I2C at the desired rate, actually faster than the desired rate. And so as we walk through this lesson, we're going to examine then how different design choices affect our program execution speed. We'll take a look at I2C clock frequency, serial baud rate, because what we're going to do in our program is we're going to read the data and then we're going to serial transmit it to another program. So we're going to take a look at how baud rate affects that, and then we'll take a look at serial print versus write functions as well. We'll start then with the first sketch, lesson 8A, right, and I'll just pop open that Arduino sketch here on the screen. So lesson 8A isn't anything we haven't seen before. It's actually just going to read information from the registers and print it out. So our targeted sample rate is going to be 1 kHz. The settings in this program will be using serial baud rate of 115/200. We'll use the I2C clock frequency, the standard mode of 100 kHz. Right. I'm including the Arduino.h libraries here because I am using the int main form of the program. We need to include the wire libraries to use I2C. And let's see, I'm using this macro, sample interval, microseconds 1000. So 1000 microseconds, right, is 1 millisecond, or about 1 kHz is what we said we want to sample it at. All right, so in main, I'm setting up my variables, calling the Arduino init function to turn on the timers. And then I call this function in our program that we wrote, right, my setup. And that is where we set the serial baud rate. We go ahead and initialize the I2C hardware, right, by calling these functions. We know that when we power up the MPU6050, the clock is in a sleep mode. So we set that particular bit to 0 so that we can turn it on. We end our transmission. I'm just going to print out a little message that setup is complete. So we see that pop up in the serial monitor. And then I call the serial flush function. That's not, the reason I want to do that is serial flush, that function doesn't return until data is transmitted. Because eventually then I'm going to end up timing some information, and I just want to know that this operation is complete before I start some other operations. So that's the only reason I'm calling that here. All right, so in main, right, when we return from my setup, I'm going to record the current time, right? I'm going to call the micros timer, which tells us how many microseconds since our program started running. Record that in sample time. We go into our infinite loop, right? And then we start querying the timer, right? If the elapsed time then is greater than, I could make that greater than or equal to, actually, should make that greater than or equal to our sample interval of 1000 microseconds, then we're going to try to read information from the data registers, right? So this is how we've been reading information before. And we'll just go ahead and print it out to the screen. So I'm just going to upload this code to the Arduino. And let's pop open the serial monitor, which pops open on the screen. Now you can see, right, we're going so quickly here that this is just scrolling by. But it looks like we're reading the information, right? The question is are we really reading this at 1 kHz? We have no way of telling that unless we start timing some information in our program. So let me minimize that. Right. And so here, right, this just shows you some example output. That's what I just said. How do we know how fast this information is being read? So what we want to do is we want to open up the lesson 8B code, which builds upon lesson A. So let me, open that up here. Right. And so we're going to add some code then to time how long these operations take. All right. Let's see. I wanted to change that to greater than or equal to. Make that change here. Let me upload the code. So to walk us back through lesson 8B is we're going to try to answer the question about how much time it takes to read the MPU6050 measurement registers and how much time it takes to serial transmit data using, sorry, that should be print, not right. And so we'll actually calculate the average time to read the data registers, and we'll print that information out using serial print. Once again, this is just like AA. We're going to use a baud rate of 115/200. We're going to use the standard mode clock frequency. So all of this is the same, right? Everything in my setup is the same. Now, at some point, we're going to change the clock frequency. So I actually have that commented out here. So this will start up by default in standard mode. Everything here pretty much looks the same as the previous program, right? Except I'm adding some variables to keep track of start time, stop time, right? And then we're going to keep track of average read time, average transmit time. And what we're going to do is we're just going to basically run the loop 5 times, get 5 samples, and display that average time. All right, so here, right, this has changed because I want to limit the number of samples I take. So count is going to count the number of samples we've taken so far. And so basically if we've taken less than 5 samples, right, if that's true, and if it's time to read, so this is still the same as the previous program. We're comparing elapsed time to our sample interval time. If that's the case, then once we come in here, we're going to record the current time in microseconds as start time. We'll go ahead and perform our normal read. And as soon as that's done, right, we'll then store the end time and stop time. We'll accumulate the elapsed time, which is the difference between stop time minus start time, into this summing variable, average read time. Right. Notice then average read time is the same type as the timers, unsigned long. Since I'm only getting 5 samples, or in some cases 10 samples, I don't expect any the sum to get too big to overflow. That's why I'm using that data type. It should be fine. And then we're going to print out, right, what our elapsed read time is. So for each one of these reads, we'll print out the individual read time. And then as soon as that's done, so I'm calling serial flush here because I also want to time serial operations. So I want to make sure that the serial operations are done before we start timing those. So that's why I'm calling serial flush there. And now we're going to then record then how much time it takes to print out this information. Later we'll add this flush back in to see how that affects that. But for right now, we're just going to record then how much time it takes to write this to the screen. And when that is all done, right, when we have 5 samples, so here in this branch, it says, okay, when our counts equal the number of samples, then just go ahead and calculate the averages and print out those averages for us, right? And then basically the loop will do nothing because neither one of these conditions will be true. Right, I think I already uploaded that, but see, I've been talking so long I don't remember. All right, let's start up the serial monitor. All right, so this goes pretty quickly. Set up, okay, so there's some old garbage from before. Here is where our code started. I'm going to clear the output. I'm going to hit the hardware reset on the Arduino board. Right, hit reset, and so let's just see the data from this one run. All right, so we see we got that message set up complete, and this is where it goes through then this elapsed read time. That's how much time it took to read, complete those operations reading from the MPU6050 registers. So 1712 microseconds is 1.7 milliseconds. So you can see right away we're not going to hit that desired sampling rate of getting a sample, getting data at least once every millisecond. Here's where serial print is printing out that information that it read. And so we can see that the elapsed serial print time on this particular operation was 1.5 milliseconds. And so the totals are down here then for the average read time of 5, right? So the average read time was 1.74 milliseconds, average transmission time 1.5 milliseconds. That's over 3 milliseconds for one operation. We're not going to hit that 1 kilohertz sampling rate. Right, let me close this. Okay, and so the other thing is why 5 samples? 5 doesn't seem like very much. I worked with this for a while, and you should work with this for a while too, right? There was a point, right, where I set this to 100, upload that. It's going to take a little bit of time for this to scroll by, not too long. And for 100 samples, we get a number that's very similar. Right, we get times that are very similar. So before you scale down to 5 and say, okay, 5 is good enough, you want to then get larger samples, right, to know that 5 is representative. So this is something you should work with for a while. I ran it at 100, I ran it at 1,000, I ran it more than once across a couple of different days. I was getting the same information. And so for purposes of making it easier to read and the fact that getting 5 samples was giving me the same information as 100, I just settled on the 5 as the number of samples here. All right, and that's what shows you here. Here's an example output of one of the sample runs. Right. And so it's very similar to what we just saw. And of course, what we just said is this 3.27 milliseconds in this case was way too long. So we want to say, what can we do to speed up the time? Right. And so we know then factors that are affecting our execution time are the I2C clock frequency. We're using a serial print function versus serial write, and it could be the baud rate as well. Now let's take a look here. I'm going to pop the program back open. All right, so let's take a look here. Now we're printing out a lot of information that, if you think about it, if part of what this program was supposed to do, let's say transmit information to another program, like we've been doing with some of our Python programs for plotting, but say we want to transmit information then to a Python program where that might use then this accelerometer and gyro information to do other things in our program, maybe to control our robot. So we wouldn't necessarily transmit all this data, right? I did this with the labels and the tabs to make it look pretty, right? So we can see what we're reading. So what if we were to comment that out? And down here, right, I said, how much faster would it be if we were to remove labels? So if we want to simulate then what we would do to just transmit to another program, we would likely just send the data. And because remember, print is sending ASCII characters, and those ASCII characters, we don't have a fixed length, right? If we have the number, if we're sending 393, then that's 3 characters. If we're sending 3093, that's 4 characters. So we don't know how many bytes are sent every time. It's not consistent because it depends on how many characters are in this number. So what we do when we use print is we use some sort of delimiter in between those bytes. So the receiving program has a way of knowing, right, what is the end of one number, what's the start of the next. And so this would be the bare bones sort of thing we'd likely use when we're using print. The last one, we'll use print ln to indicate that that's the end of the message we're sending, the carriage return and line feed. And so let's go ahead and upload this. And let's run it. All right. And so our average transmit time before was about 1.5 milliseconds. Well, now it's about 1.23 milliseconds. We did save a little bit of time by getting rid of that extra information, but we're still at the point, right? Well, I2C is definitely way too slow. We sped this up, but we're still not going to then be able to hit our desired sampling rate, right? And one other thing while we're here is sometimes, some of you, as you've been working with your homework, the serial doesn't seem to be keeping up, right? You've had some errors over on the Python side. It seems like you've lost some information that's coming across. So one thing I said that you could try was over on the Arduino side, go ahead and flush that information, because flush guarantees this function will not return until the serial transmission has been completed. So that way you shouldn't overwrite data, because there is a fixed size to the buffers for transmit, right? And it is possible to overwrite data if you're transmitting fast. So if you're filling those buffers faster than it can transmit, that is possible. There are flags that can be checked for that. So here I'm adding in the serial flush. Let me upload that while I'm talking. And let's run that, and let's see how much time the serial flush adds if we put that in. The serial flush then takes some extra time, right? Before we had 1.2 microseconds with this code, 1.23. Now we got 2.8. And so if you run this with serial flush, you'll see consistently that calling that serial flush adds some time. So that's not always a good fix for execution time. So I'm going to comment that back out. Put this back to the state it was. I just guess not all that important to save it on my computer in that state. All right. So experiment with this, right? See how your choices affect things. All right. So the next thing we're going to want to open is .8c. And open it on my other screen. All right. So what we're going to do now is let's start by changing the fast mode clock frequency. Right. So actually what I should do is change that within the program we just had up. So sorry, I told you to go to 8C. Let's go back to 8B. So I get this over on this screen. All right, so that was the other thing I wanted to try here is wire.set clock. All right, so now we are going to increase the clock speed to 400 kilohertz. I should comment this out. Let's just go ahead, right? We saw that this stuff without printing, right, the labels and tabs, because we likely wouldn't print the labels and tabs to other programs. Serial flush is turned off, right? So the fastest serial we've seen from this one, and speeding up the I2C clock by calling the set clock function and passing it 400,000. L stands for long, making that constant along. Okay, let's run this. Significant change, right? 545 microseconds, or 0.54 milliseconds. That puts us under that 1 millisecond rate for reading information. We still have to contend with the serial, right? We still haven't gotten the whole program execution down to less than 1 millisecond, but that was a huge change. All right, so I gave you an example in here, right? Here it happened to be 544. It sped things up about 3 times faster. Right? So we changed that clock rate. The clock rate was the clock rate's 4 times faster. It only changed our execution time about 3 times faster. But remember, there's some overhead in terms of calling those functions, right? Pushing things onto the stack, right? There's overhead on the processor. So that's why we didn't have a 4 times speed increase likely. Right. This is where I said we can get rid of the labels. We've already done that, right? We've already improved our times as much as we can. And we want to start taking a look at, well, serial print, right? We can say, well, is the baud rate slowing our transmission? Right. So if we're sticking with serial print, let's just go ahead and take a look at what is the worst case for the number of bytes transmitted with the above code. Well, we know that an int 16, a 16-bit integer is a signed value, so it could transmit values anywhere in the range from -32,768 to +32,767. Right. Positive numbers don't transmit with a plus sign. So our worst case would be 6 characters, right? The negative sign, 32768, 6 characters. Right, 1 character requires 1 byte for serial transmission, so we have 6 bytes. And then we have the commas as well in between. So each comma requires 1 byte. The print line sends, I don't know why that's saying TE. It should say, right, the carriage return and the new line byte. I'll have to correct that. Well, let's take a look. So we've got 7 measurements, right? Acceleration X, Y, Z, temperature, gyro, X, Y, Z. So 7 measurements times 6 bytes is the worst case for each one. And then we've got 6 commas that each require 1 byte. We've got the carriage return byte and then new line byte at the end. So we're sending 50 bytes. That example code that we were looking at was sending 50 bytes. This code here. That's worst case. Not every time, worst case. 50 bytes, 10 bits per byte. Remember, each byte has a start and a stop bit with our serial communication, so 500 bits. And so if we expected 1,000 transmissions, so 1 kilohertz, right, 1,000 transmissions per second times 500 bits per transmission, that's 500,000 bits per second. Right, a baud rate of 115,200 is only allowing 115,200 bits per second. Right, that's another bottleneck to our execution time. That's slowing our program down. So we could increase the baud rate, but we could also try to more efficiently transmit data with a serial write function. Right. Remember, the serial write function is only going to transmit 2 bytes. Right. No matter what number is stored in this 16-bit integer value, right, whether it's signed, unsigned, because it transmits data as 2 binary bytes, we're always going to consistently transmit a series of 2 bytes for each one of these values. And so now if we take a look at, and I said this is better than our worst ASCII case of 6 bytes. 2 bytes is better than 6 bytes. Right? We don't need the comma delimiter. So that's the other thing. When we use serial write, the other program that's receiving it, when we know that we're transmitting in binary, we can just say, okay, let's extract the first 2 bytes. That's one number. The next 2 bytes is the next. So we also don't need that comma delimiter. So that saves us some information that we have to transmit. So if we're going to use the serial write function, we'll still have our 7 data measurements per transmission. There'll be 2 bytes per measurement, so 14 bytes per transmission. Right? 14 bytes per transmission times 10 bits per byte. That's 140 bits per transmission. That's better than that case we saw up above, that worst case of 500 bits per transmission. Not every transmission would be that big. That was our worst case. But we know then that this will always be 140 bits per transmission. Right? And so 140 bits per transmission times 1,000 transmissions per second is still 140,000 bits per second. Right? That's still faster than our 115,200 baud rate. We may need to increase the baud rate as well, right, in order to achieve this. Let's go ahead and look at lesson 8C, where we're going to use the serial write function, and we're going to measure that transmission timing. All right. So let me pop 8C up to the screen. All right, let me correct that. Should be greater than or equal to. By the time you see this in the repository, it will have the greater than or equal to sign in it. All right, so same thing again. We're going to try to read and transmit data at a sample rate of 1 kHz. What we're going to do is we already know that we should be using this 400 kilohertz clock frequency. We need that. We're keeping our baud rate at 115,200 because we want to make one change at a time in our program. So the first thing that we're going to change is the serial write. Everything in this program will be the same, the baud rate, the clock frequency, as what we just saw in that previous example, where we had achieved with this clock rate about a little more than half a millisecond of read time. And this was serial print. At this baud rate, we were getting about 1.2 milliseconds for our serial print, where we'd scale that down. I don't know why. I have some extra characters there. So we're still going to print out setup complete. I've got a short delay in here. All right. Now there are some differences here in terms of the data that we read. I'm going to store in a buffer, right? It's still going to be, right, a signed 16-bit integer. So a buffer, or this array that contains 7 for our 7 measurements: accelerometer x, y, z, temperature, gyro x, y, z. Well, actually, you don't need to initialize it. So I had initialized this in an experiment where I was printing out this information to make sure my pointer information was correct. I'm actually going to get rid of that there. Well, let me tell you about that, and then I'll get rid of this. All right. So we're going to read the data and we're going to store it here. Before, we had separate variables of AX, AY, GX, GZ, AZ, and so on. Everything here looks the same. We're still going to take 5 samples. We're still going to read from the registers. But before, right, instead of data 0, we had XLX, right? So we're still going to have the same number of read calls, right? We're not changing the number of function calls. All we're doing is changing then the name of the variable that we're storing that information in. The reason I'm doing that is when we go ahead and we then perform our serial write. So here, the serial print information, that's just going to print information to the screen, right, so that we can see the timing, right? I'm going to make sure that we flush that at the end so that before we start timing these serial operations, we know that all of the previous serial is complete, so that we're not timing anything that occurred previously. And so here, right, when we want to write all of that data, we can simply then use the serial write form that expects us to have a buffer here and say the number of bytes. Well, here is our buffer, right? Our buffer is this signed 16-bit int type named data. Well, knowing a little bit about pointers and programming that you may not have used before, some of you probably have, you can actually, because the name of an array is a pointer in memory, I can actually then use this typecast here, didn't mean to do that, and say I want to cast. So when I use this name in code, if I use it all by itself, it would have been in, so the name data is int 16-bit underscore t. So that name all by itself then is of this data type as a pointer to a 16-bit integer. I need this to be a pointer to a byte. I just want to transmit the binary information. Doesn't matter whether I'm telling this to say, hey, this is a byte pointer. Don't think about it as being unsigned data. It's just a set of binary digits in there. I need to say that this is a byte pointer because serial write expects this to be a byte type buffer. When I say it's a byte pointer and I say that this should read 14 bytes, it will access this in memory 1 byte after the other, and it will correctly transfer the data, right? Simply because these are stored contiguously one after the other in memory. So using an array allows me then to just issue the one serial write command. I'm going to typecast this to the correct pointer so that I'm not getting warnings, and it will actually read the data correctly. Well, the reason then I had the 0, 1, 2, 3, 4, 5, 6 here is I ran a little experiment before, and so maybe we'll just read that now, run that now. Is here, I just said serial.write, and same thing. I want to cast this as a byte pointer, data, and I want you to write 14 bytes. And what I was hoping to see was the 0, 1, 2, 3, 4, 5, 6. And actually then what we can do is we can just issue a while one here so our program doesn't go any further. I'm going to upload this. And if I were to pop open the serial monitor, we're just going to see garbage. Actually, I don't see anything. Why not? Should have seen setup complete. Should have had the delay. And the other. There were no warnings or errors. Make sure Baud rate's 115,200. Clear output, do a hard reset. Now, this is why you never do anything different while you're creating a video, because of course it doesn't work. And I want to close that window. What I was hoping to show you was that this is just going to show up as gibberish here because it's going to try to create, it's going to use those numbers as ASCII characters. We should see the setup complete. What I'm going to do is start a program called QCOM, which is a serial terminal emulator you can install through Ubuntu, sudo apt-get install. Sorry. QCOM is the name of it. And so you can open a connection to the serial port, right? I don't have a serial monitor open. You can go to settings here. When you first download this and install it, you probably won't have this path. So I had to type in this path here. You can go to settings. So you can set your baud rate here, because I think by default at first it's 9600. These are usually the same, 8 data bits, no flow control, no parity, open it for read write, stop bit. So all of this is fine. You usually just have to change the baud rate. And then when I click on open, I should open my connection to the Arduino, which I don't know why I've lost that connection. Really don't know why. Of course, worked yesterday. Is there a problem with me going into the infinite loop? We start up the serial monitor. We've got nothing. Right. I am going to end this video right here, and then I'm going to find out what's going on with my Arduino so you don't have to suffer through this. Actually, I think I can pause recording and I will come back. All right, I've come back. I took a look at, the state of my USB connections and all on my Linux device. I wasn't seeing any errors. So I did actually, I also tried to troubleshoot by going to one of the examples, write file, examples, communication, ASCII table, and say, okay, can I just go ahead and upload this code and run it? I got nothing out of the serial monitor. I was trying to rule out a code problem. So I finally did unplug the Arduino board from the USB port, plug it back in, ran this sketch, right, uploaded this. So this is AC, and it worked. No good explanation of why it didn't work before. All right, so let's take a look at, so this is 8C as you'll find in the repository. And so if you run it with a serial monitor, you'll see this information set up complete. It'll show you the elapsed read time, but it shows you garbage here. Remember, this garbage is due to the fact that we're using serial write. The important thing is, right, we see that we don't have a change. Remember, then our fast mode clock for I2C was 400K hertz. So this is still around our half millisecond time. But look at our transmission time. Our transmission time in this case was 105 microseconds, or about 0.1 milliseconds. So if we add these two operations together, right, time it takes all of this code to execute, we should be able to now achieve our rate of sampling 1,000 times a second, because this takes about 646 milliseconds. So 0.646 milliseconds, less than that 1 millisecond time. So without even changing the baud rate, which we said we thought would be too slow, right? Because we have some time savings over here in the read, the overall, this code is going to work for us, right? In terms of the timing we want of our 1K hertz sampling rate. All right, so this is that lesson 8C as it was. Like I said, what I was trying to do here is I was actually then trying to print out information. So serial.print ln, I'm going to say array contents, and I wanted to say serial.write. I'm going to make this a byte pointer, data 14 bytes. That's what I was trying to show you. Serial.flush, and that delay, let's delay a second. And I really don't want to go do anything else. I really want this while one do nothing. See if I can upload this and let's see if it cooperates this time. Interesting. What kind of a mode do I put this into? See, I put the Arduino into some strange mode, or the connection. Really didn't have this issue the other day. My whole point was to show you the data that comes across here is correct. We will see the 0, 1, 2, 3, 4, 5, 6. I could write this as a separate program. I'd see if it behaves better. I'm not quite sure why this is happening. I'll save as. And of course, my menu pops up on the other screen. Let's just call this temp right now. I don't care about any of this. I might care about that. Oh, I know why. I'm being completely stupid. And I'm trying to do all of this before I call init in my setup. Yes, so you all probably saw that quite a while ago. Probably just yelling at me about how stupid I was being. So while we're here, let's just put this in the right place. We don't need any of this other gobbledygook, right? Because this was just supposed to be an example that shows us we're going to see the data we want to see. Here, don't really need the delay. I'm just going to say while one semicolon, or I could have. So let's see if we can upload this, and hopefully, yes. All right, and clear output. I had old in there. I hit the hardware reset button on the Arduino. We see setup complete, array contents, and then it can't print these numbers, right? Which is why I went to QCOM the other day, because I wanted to see those numbers. So once again, I am going to start that QCOM application. Set FTTY ACM 0. My settings are already at 115, 200 baud. I'm going to open the connection, right, which then triggers a reset. So now we can see, right, what's coming over from the Arduino. Setup complete, array contents, these breaks that were sent, probably relate. Well, I can see there's my, you can't see, this is tiny. This is CR, LF, so carriage return line feed. I'm not really sure where these breaks come from, honestly, but what's important, what I wanted to see is I wanted to see the hex 1, 2, 3, 4, 5, 6. This might just be a line break in QCOM because I've asked it for line breaks. Not quite sure. The important thing is, let me minimize this a bit. Remember what I said is my point was is when I did this, I wanted to show then I wanted to test to make sure that what I was doing with this pointer would actually send the data I expected, which is why I initialized this to known values. I had this little test program here, then that simply just prints out the array contents. I need QCOM to be able to see them because it will actually show me the hexadecimal values versus the serial monitor in Arduino. Something else you can do if you want to see all of the hex output, you can hit, you can check hex output. So I'm going to hit the clear button here. I'm going to hit the hardware reset on the Arduino to start the program over. And so if you want to see every hex byte that's coming across, it will show you all of that. It will show you the ASCII over here to the right if it can. So setup complete. If we were to go in and look at the lowercase s, I'm going to guess the lowercase s is a hex 7.3 in ASCII. That the E is the 6.5, the T is the 7.4, right? And by default, this only shows you so many characters on a line typically. What's important here is, right, and sometimes this goes over, so this 0 might be related to a break, but look, here's this 0001. That is likely then the 2 bytes for this 0. And bring this back, potentially the first 0 was only this set of zeros. It's still not fun to trace this sometimes in software, right? But I'm going to think this 0002 relates to this 0003 relates to this 4, 5, and 6. This 00 is probably what we're seeing as a break on the other. And one thing we could do is here, clear. What I could do is maybe this will help if we make this 1, 2. Well, that was supposed to be 2. 1, 2, 3, 4, 5, 6, 7. Let's upload this to the Arduino. We can't. Notice I got an error because I didn't shut down QCOM. Well, if I just close that, I don't have to shut down QCOM. If I just close that connection, that serial, now I can upload. All right, we uploaded back to QCOM. Let's open the connection. All right. All right, so there's, see, I'm still missing the 2 zeros that I would expect there to be between the 0, 1, but here's my 0, 2, 3, 4, 5, 6, and 7. So what I am just going to think, right, is that somewhere in the software interpreting this, I'm still going to go with the theory that my data, by creating this to a byte pointer, is going to go across correctly, right? So that was the point I wanted to make with that before we got off on this kind of long tangent. QCOM is one of my favorite Ubuntu serial terminal emulators. There's others, there's PuTTY, there's plenty of others. QCOM, I think, was one of the first ones I worked with, and I enjoy, it's easy to work with. All right, so that is finally the end, I believe, of this long lecture video, right? If we go back here to the repository, right? This is what the rest of this text talks about. It shows you the time. And I said, at this point, it's now left as a student exercise for you to test how changing the baud rate would affect the execution time. And so remember, if you start increasing the baud rate, you need to go out and look at the microcontroller, the data sheet, as we did in the first homework, to see what the error rates are associated with various baud rate settings. So if you increase it, go ahead and try increasing it to some of those other settings. See if you get better times, worse times. You might get a worse time if there's errors associated. So just go ahead and try that. Let me know what you get, right? Share that information with me, with your classmates, right? So hopefully now you can see that when you write code and we're working with time-sensitive data, when we're working with something, right, where we need to sample it every so often, we just can't make the assumption that that is happening. We have to look at what clocks we're working with and what settings we should make in order to know that we are able to sample the data as quickly as we want to. Now, it would have been possible it might be entirely possible that we can't achieve that, right? We only have limited settings in our software and working with the Arduino microprocessor, right? The gyro that can be sampled at 8K hertz. Well, we might not be able to achieve that. We would have to go out and work with our software, time it, and get an idea of what can we reasonably achieve, right? If it's something less, if it's say only 600 hertz, then we have to then know that and factor that in to everything we write and our decisions that we make in relation to our application. All right, well, thanks for viewing, right? Run this code, experiment, let me know what you come up with. And trying to get to this. Yeah. So I'm trying to turn off the recording and Zoom is not responding.